a talk.
Thank you very much. We are very happy here to be in Bergamo, the beautiful city in Italy. And in our talk today, we will discover how to find local privilege escalation bugs on Windows, both via reverse engineering and advanced fuzzing techniques. And if we want to sum up the talk in 10 seconds, is kernel fuzzing, kAFL, plus drivers equals many, many bugs and profit. So before we dive in, a bit about ourselves. I'm Shimony, security researcher at CyberArk, primarily focusing on finding local privilege escalation bugs and on drinking cocktails. And there is a strong correlation between the two. The more cocktails I drink, the less bugs I find.
Hi, I'm Mark Cherp. I'm also a security researcher from CyberArk. I work with Iran. I'm mostly into low-level stuff, fuzzing, and rock climbing whenever life allows it.
Okay, so what do we have on the menu today? Well, we will start with the question that every security researcher asks before he tries an offensive research, and it is what to attack and how. We will dive in later to some Windows internals, enough to understand the bugs, but not too much to make you fall asleep, which we will cover later with shallow deep dive into the bugs. We will continue with automation, how to discover more bugs and faster, and eventually we will warp things up with some kernel specifics and our kernel fuzzer, kAFL, with some tweaks that we have done. Okay, so what do we want to attack and why? Well, we said earlier that we mainly focus on local privilege escalation vulnerabilities, and drivers are good candidates for that because in some occasions they are interactive from regular user standpoint, limited user, and Windows is the perfect place to look for bugs because there are more than 300 different drivers on Windows out of the box. All of them are written in C, some of them can be dated to the 90s or the early 64-bit days, and that's not including third-party drivers. If you include them, you probably have more than 400 drivers on a regular Windows machine without any custom crazy drivers. Also, Windows is considered to be a closed source operating system, even though you can argue about that because of all the recent code leaks. But if we find a strategy that works well on Windows, we can probably take it away to other open source operating systems like Linux and Android, for instance. So let's go to some Windows internals, and this is the world we are living in. You can find this slide probably in any Windows privilege escalation talk, and it showcases the different privilege levels, the trust levels that you have on Windows. We start either in a sandbox application or in a non-admin process, and our goal is to run code either in the kernel, that's the best case, or in an admin process or a service. And in this case, our attacking vector is drivers. Well, what are drivers? On Windows, drivers are an extension of the Windows kernel. They reside in the same address space, the system address space, and they have the full might of the Windows kernel. Therefore, they can call almost any API that the Windows kernel is willing, but they share the same responsibility. So if you have uncaught exception in a driver, it will crash the kernel, unlike user mode applications, which will just crash the application itself. Also on Windows, drivers must be digitally signed. If it wasn't the case, then a malicious actor that had admin access could just load the driver, and by doing such, having a rootkit and bypass any security mitigation and, of course, any product that you can have over your machine. And the responsibility of drivers is mainly talking to hardware, devices, and doing filter activities to I/O or networking. And of course, not blue screening your own machine. It's also a very important thing that was a plague of the past in the early Windows days. But we have some problem. Windows offers a multitude of driver modules and frameworks. Out of all of those, which one do we want to focus? Because we are in the bug hunting business, and to find more bugs, we must focus. Well, we chose WDM. WDM is considered to be the oldest driver model out there. And besides that, there are two prime reasons we chose to do so. One, it's very difficult to write a secure driver in WDM. It was first introduced in the 90s, and if you know, in the 90s, security was not a concern of anyone, especially not vendors that just want to make money. And also, its usage. Its usage is the most abundant of all the other driver frameworks and models out there. Over than 70% of the drivers are written in WDM, hence more than 200 drivers out of the box. So let's go through some bug hunting 101 in drivers. And also in this case, there are two main things that we need to know when we look for bugs. The first one, to which driver I have access to out of all those 200 drivers, and what are my permissions? Can I write, can I read from the device? The second thing is, how do I communicate with the driver, and later, how it parses the data I've sent in from user mode. And as you probably know, most of the bugs out there are about parsing errors or logical bugs in that area. So we need to first answer those two questions to understand if we can find a bug. Well, the first thing is access. On Windows, you do not talk directly to a driver. You talk to it through a device it creates and later on exposes. The way it does it is by calling either IOCreateDevice or IOCreateDeviceSecure. And in the latter, you can specify a string that restricts the access groups that can interact with the device. If you don't do it, then anyone can open the device and interact with it. After that, you must call IOCreateSymbolicLink or IORegisterDevice interface. What it does, it registers a symbolic link in the object manager. The device object also resides there. And that allows the user to open a handle to it by calling createFile or anti-createFile. And after you have the handle, you can interact with it. So here is an example of some drivers and some devices it exposes. In here, we can see a driver called vid.sys, that creates two devices and exposes both of them to the user. And if we look on the second device, videxo, we can see that the permissions are very permissive. Anyone can interact with the device. And actually, in this driver, we found a very cool bug that resulted in a crash to the hypervisor. So that was a very nice finding and a very simple bug, but we won't look at it at the moment. You can later ask us about it. So the second thing, as we said, is the communication. Now, in Windows, the entire communication or the backbone of a driver is the driver object. Now, the driver object registers something called dispatch routines through a function pointer array called major functions. And those dispatch routines are being triggered whenever you do an operation over the device. For instance, if you call anti-createFile, it triggers a dispatch routine for the create. Also for close, for read, and for write, and for more. But in our case, the most important one is device I/O control, or the anti-DLL counterpart, file I/O control device. Why is that so important? Because we have a large flexibility in the parameters that we can send from user mode to the kernel through that operation. Now, those dispatch routines are the go-to places to look for bugs in drivers, because all of them, if you have access to the device, can be triggered from user mode, which is excellent if you can actually make some code run in the kernel through a simple API calls. So talk is cheap. Let's see some code. This is a typical driver entry on Windows. And we can see that the first yellow box demonstrates a call to IOCreateDevice, and it just creates a device without any security descriptor, so any user can has access to it. And on the latter yellow box, we can see the driver enlists a dispatch routine for the device I/O control routine. It's called testy dispatch ioctal. Also, you can see that below it enlists more dispatch routines for other operations that can be done over the device. But you probably ask yourself, how does a dispatch routine looks like? Well, every dispatch routine has the same signature. All of them receive two parameters. The first one is a pointer to the device. And as we've seen earlier, the driver can expose more than one device. So there could be several devices associated with a driver, so we get the pointer for the device we did the activity on. And secondly, and the more important data structure, is an ERP. In this case, we receive a pointer to the ERP. Below, in the second yellow rectangular, we can see something called IO control code. And if you are familiar in Linux, it's mostly called an ioctal, and we will examine it shortly. But what does the ERP has in it? Well, the ERP is the means of communication. Think of it like a data packet that holds many important data structures that every dispatch routine might need, and almost any parameters that it will ever need. And the driver receives a pointer to this structure. In some cases, the data resides in the kernel memory, and in some other cases, in user mode. So let's examine a few of those members inside the ERP. The first one is a stack location, which holds many important members, but we won't talk about them now. A second one is a requester mode, which means if the ERP was generated in user mode or in the kernel. In the kernel, you can also generate ERPs and communicate with other drivers. Also, you have buffers. Some of them reside in the stack location and some of them in the ERP itself. It depends on the transfer type that we will see shortly. And lastly, but not leastly, an IO status information, which indicate how many bytes are to be written to the output buffer in case of success. This is a prime source of information leakage, and we will see an example of that. And every misuse of one of those parameters would arguably cause a bug. So driver developers must be super aware what any member of that is doing, unless they want, of course, to uncover some bugs to their clients. So how can we generate an ERP? We said earlier, API calls that we are doing on the device, and we can see here that the first argument is a handle to the device we're doing the operation on. And the second one is very important. It's the ioctal code. And the reason it's so important, it's the way it affects the four next parameters, the input and the output buffer and their respective lengths to the dispatch routines in the kernel. So the ioctal code is a 32-bit integer numbers, which is a bit field, if you're familiar with it in C. But we only care about 4 specific bits in it. The 2 least insignificant bits, bits 0 and 1, and the 14 and the 15 bit. They indicate what is the required access and how we actually transfer the data from user mode to the kernel. We will start with the easy one, which is the required access. Now, the required access, as we said earlier, it's 2-bit integer, and it describes the required permissions to send to the device IO controller request. And it corresponds to the permissions you open the device with. And you have 4 different options, of course, because it's a 2-bit integer numbers. If you don't have the relevant permissions and you do on a device IO control request, then the IO manager, the kernel, will kick you out and your code won't be triggered in the dispatch routine in the kernel. Now, the second thing, which is the prime source for so many bugs in the Windows kernel, is the transfer type. Now, the transfer type describes the way the driver will get the data from the user mode. So if you do not understand correctly what every transfer type does, you probably won't use those parameters in the driver correctly. And if you don't use the parameters in the drivers correctly, you're probably going to blow your own machine. And also in here, you have 4 different options: method neither, method buffer, indirect, and out-direct, and we will examine them now. So after this introduction, we will go to some basic bugs and some code, of course. So the source, the matter of all evil, as I call it, it's method neither. Let me remind you, it was developed in the days that security was not existent. And in this case, the IO manager is lazy. So you have no copying to the kernel itself. All the buffers and their lengths resides in the user space. So the driver only gets a pointer to those buffers. As a result, the user can change the buffers in between, and the kernel won't, of course, know about it. You can allocate and deallocate the buffers, and if you refer to invalid memory in the kernel, then you're in a shitstorm because that will cause a crash to the kernel because you touch an invalid page. And if you have uncaught exception in the kernel, then you have a blue screen. And that's a very probable bug that happens if you do not access those user mode pointers inside the try except block. Besides that, of course, it's not enough just to access them in a try except block. You must capture the buffer inside your code because the user can change it between usage, leading to some very nice race condition bugs that can come from that. But one way to circumnavigate those type of attacks is probing. Now, probing sounds very nice, but it actually does not touch the memory of the buffer. It just takes the address of the buffer, increments it by the length, and checks if the address resides in the kernel space or either in the user space. If it resides in the kernel space, then it throws an exception. And of course, you must call the probe for read and probe for write operations inside the try except block. But that's OK. You deal with it in your exception handler, and you continue your life. But if you use those functions without an exception handler, and you send the kernel address, then it will, of course, crash the system because it's, again, uncaught exception in the kernel. One of the problems is that if you trust user mode data blindly, and you take the length, for instance, from the input buffer length, and the user sends it of the value of 0, then the kernel thinks, OK, the size is 0, so I don't need to do any checks. And that's one of the caveats on the Windows kernel, that it's pretty lazy. So if you use those APIs, you of course need to sanitize the length field before that. But what happens if you do not use those APIs? Well, the best case is if you touch an invalid page, it will crash the kernel. But if you try to read from a kernel address and you later on return it to the user mode, you probably can face an info leak of kernel leak memory. Or if you try to write to it, you might reach to a dangerous situation of arbitrary write. And if you have those two primitives of info leak and arbitrary write, you can probably own the kernel and run a system shell out of that. So a quick example of that is a driver made by Realtek that you probably have on your own Windows machine. And I think the same vulnerabilities applies to Linux as well, because Realtek also installed on Linux. And in here, we can see that the ioctal code ends with the digit 3, which indicates method neither, 1 and 1. And we can see that we do not have any try except block in this entire code. So any usage of those buffers are not done in a secure manner, so the user can swap them whenever it wants. Also, we can see that on the second yellow box, that we reference an input buffer, but we do not check its length whatsoever. So if it's a null buffer, then we are doing a bad thing. Also, on the third yellow box, we can see a reference to the output buffer. Again, no try catch. And later, it's not in this function, we can see that the driver writes to it, which will cause an arbitrary write. And on the fourth yellow box, we can see a dereference to the input buffer, again, without any length check, which will cause a null pointer dereference in case the buffer is null. Well, the second transfer type is considered to be the more secure transfer type, method buffered. In this case, the last two insignificant bits of the ioctal ends with 0 and 0. And in here, the IO manager copies the buffers to the kernel space and provides a pointer in the ERP. So you are not longer in a fear of allocating and deallocating types of attack. The user cannot alter the buffers as well. So no need to probe the data. But in many cases, the input buffer, the output buffer, they actually construct a struct. And in this struct, you probably have something like pointers, addresses, and lengths. And if those addresses can be controlled by the user mode, of course, you need to treat them with care. And in this case, the input buffer and output buffer resides in the same place in memory, which is in IRP associated ERP system buffer. But there is a very small caveat, but very crucial caveat to method buffered. There is this subtle case. We said earlier that IO status information indicates how many bytes are to be copied to the user's output buffer. But if the output buffer is larger than the input buffer, and the IO status information is larger than the input buffer information length, the delta copied to the output buffer is uninitialized data, besides the length of the input data. So the kernel can leak a huge amount of memory in the delta of the output buffer length and the input buffer length. In the example below, we can see that if the output buffer length is 1000 hexadecimal and the input buffer length is 8 bytes, and this later is assigned to IO status information without any sanitization of the output buffer, then we have a leak of almost 1K of data. And on a live example, well, we can see here the I octal ends with 4, indicating method buffered. On the second yellow box, we can see a very nice if that says that if the output buffer is larger than 10K, then you call a function below that fill up the output data and reset it with 0. But if you go into the else block, you have a direct assignment of this huge number without sanitizing the output buffer. As a result, you have a leakage of around 10K data from the kernel. And you can call it round robin, and eventually you can read the entire memory space of the kernel. And if you have such a powerful primitive in the kernel, you can probably later extract the SAM file, for instance, and do some rainbow attacks over it and get the password of the administrator user. Yeah, so arbitrary read is very dangerous in the kernel. And lastly, and the most complex type of transfer type that we will just touch, it's called MDL or direct I/O. It refers both indirect and outdirect. In simple words, an MDL describes a buffer in a fixed position in physical memory, which is always page. This allows it to have a huge performance increase over a method buffer that requires you every time to copy the data into the kernel. And in here, the user gets a pointer and the kernel gets a pointer, so it's kind of a double mapping to a physical page. So the only difference between indirect and outdirect is which buffer is always in a fixed position in the physical page. The first buffer is also in system buffer, and the second one is accessible by IRP MDL address. Now the kernel can also request to create MDL by calling IO create MDL, followed by locking it by mmprobe and lock pages. Now, if you try to lock an invalid page, it's the same stuff as earlier. You try to reference an invalid memory, and it will throw an exception. So again, you must adhere it and put it in a try except block. But in most cases, the people that use this type of functionality in the kernel, they do not do security checks on it. And in here, we have some case of IO allocate MDL, and we can fully control the virtual address that will be later called. So we can give, for instance, the value of 0, and later on the second yellow box, we will try to lock the address of 0, which is an invalid address, causing the kernel to crash. So that's it. That was the end of the first part, and now we will continue to the fun part about fuzzing.
Hi, welcome to the second part of our talk. I'll just start by saying that the first half was the more code heavy and the more technical part. The second part is going to be more high level, so sit back and relax as we start. So we went over the actual bugs and vulnerabilities that we discovered, and now we're going to discuss the methodology and the setup we used to allow us to do so. So let's begin. Well, first of all, as we said, our target is Windows drivers. Now, Windows drivers, we talk to them using a device. So before we start to attack something, we need to have the devices. So our first task was to try and extract the device. Now there's lots of public code and tools available to extract the device, but not really the device name, and furthermore, the actual yoctals inside the driver. So let's start with extracting the device names. This is the easier part. Essentially, what we do is we get all the devices from the object manager. There's actually a Windows API to do that. Once we've done that, we aggregate all of the names, and we try to determine the maximum permissions. Now, we do that with a fairly simple iterative process. We start from we try to talk to them dynamically with the highest permission possible. If we see it works, then great. If not, we try it with lower permissions, and we do that until we determine the highest permission possible. Now, the yoctal discovery is somewhat more complicated. Essentially, what we want to do is to statically analyze the target driver and eventually discover the yoctal codes. So to do that, we start with the driver entry function, which is sort of the main function of a driver. We track the driver object inside of it, and we look for the place where the driver object is used in order to assign the yoctal dispatch routine, as we've seen in the first half. Once we found the yoctal dispatch routine, we track the actual yoctal code, which is one of the parameters passed to that function. Eventually, what we try to do is to find some conditioning on that yoctal. By conditioning, I mean a switch statement or maybe some kind of if, because that's essentially how the driver determines how to handle the specific yoctal. Once we found all the yoctals, we aggregate them and we test them dynamically to see that we can have an actual communication with them. Once we have all that, we proceed to the part of our harness generation. Now, the cool thing about yoctals is that they have pretty much a determined API. I mean, we know how to talk to them. So we can start with some standard template of a harness. And then, with the things we discovered in the previous process, we can actually update the device names, the yoctals, and we do some simple input validation. You can think of it as sort of a very, very basic grammar. Once we have all that, we run it against our target. We'll see in a moment how this harness actually looks like. All right, so just to summarize the process, we discover the device names, we discover the yoctals, we generate a harness by updating an existing generic harness, and eventually we fuzz. All right. So before we proceed to see how the harness actually looks like, a few words about grammar. Once we've seen that we can discover the bugs using a fuzzer, even with a simple grammar. By simple grammar, essentially, I mean that we check for some specific structures or for some specific magic. For example, if we know that the past buffer should start with a specific digit, we can look for that digit, pretty much a regex. So we thought, how can we further improve on that? Because we know how to talk to the yoctal, but we don't really know what happens inside. I mean, the buffer we pass to it, we don't really know how is it going to be deserialized or how is it going to be treated. So in order to do that, that's actually where grammar could come in and help us to determine the actual structure we need. So let's see some approaches for grammar. So the first one is the most simple approach, which we're already using in our input validation. Again, you can think of it as sort of a regex or a wildcard or pattern matching or whatever. Basically, we know how the structure should look like, and we try to match it. Of course, in order to do that, we need prior knowledge about the driver, and we need to reverse engineer it. A bit more advanced approach something called input, is based on something known as input to state correspondence, is basically the idea that when we give to a certain program the input, the way this input looks like in its initial input state will probably correlate with the data during runtime. So to be more specific, for example, imagine if there is a program that receives some sort of an input, let's say seed value is our input, and at some point in our code, we see that a register, for example, EAX, is being compared with some certain value. And then eventually we observe that EAX has part of our input. So obviously we can understand that our input affected the register. Then we can replace the register with what the compare instruction actually expects and see that we probably will discover more code paths. Now, another approach, which is based on large mutations, as they call it in an article about Grimoire. So the idea is that basically we can use the same strategy of small-scale mutations, as it's usually done with regular fuzzers, but we can do it in a larger scale. So to explain that, imagine, for example, that you have some sort of original statement, which is like print A, B, B, C, D, and then there's a slight mistake in the slide, but then the idea in the mutated function, for example, imagine if I would eliminate the first two A's. If I would eliminate the first two A's, if what we're fuzzing is the Python interpreter, it probably will not affect the code path because the Python interpreter doesn't really care what string is in there. On the other hand, if I were to eliminate, for example, the two letters P and R for the print, it would be an error as far as the interpreter cares. And then probably some kind of a other code path would be triggered. Now, we're still working on choosing the best strategy on grammar. We tried a bit of all of them. Currently, our intention is more to go on the large-scale mutations, but of course, we'd be very glad to hear your thoughts on that as well. All right, so after talking about the automation before the actual fuzzing, let's discuss our kAFL fuzzing setup. So basically, that's the architecture. Now, a few words about virtualization. In order to use kAFL, the idea behind this is that the fuzzer is actually being executed on the host, and the target is being virtualized. Now, as you can see on the slide, as far as hardware requirements, we need Intel VTX, which is Intel's hardware support, and Intel PT, which stands for Intel Processor Tracing, which is basically the ability to trace each and every instruction executed on the CPU. For those of you who are familiar with it, it's sort of a built-in JTAG support, if you will. On the kernel level, we have KVM. It's being run on top of KVM. And what happens is that the fuzzer is executed as a regular process on the host. We use QEMU to virtualize Windows. We run a harness inside of Windows. Harness is basically our agent that gets the inputs from the fuzzer and sends them to the Windows driver. And the way this happens is that they both share the target guest and the host. They have shared memory, and that's how the inputs, the mutated inputs, are passed from the fuzzer to the target. Okay, so why to virtualize in the first place? There are several good reasons to do that. Perhaps the two main reasons, first of all, that we have pretty good crash protection, because, for example, imagine if you were to fuzz the Windows kernel directly and you would trigger BSOD or whatever, all of your fuzzing input might be lost and the triage would be very difficult. In our case, it will not affect the fuzzer at all if the target crashes. On the contrary, we're hoping for the target to crash, of course. We'll see in a second how this actually happens. And of course, Windows is closed source. I mean, despite several leaks, it's still closed source, and we really did not want to try to instrument and compile the Windows kernel. All right, so a few words about fuzzing. You probably heard it mentioned a couple of times today, so just one more time. I'll try to do it briefly. I want to address two specific concepts: feedback and fitness, because that's where some of the main differences between regular AFL and kAFL lies. So feedback is basically our desire to get a feedback from the target execution state. You can think of it as the edges we cover or the blocks. And fitness is how eventually when we get this feedback on the execution state, how do we decide to proceed with it? So usually the metric is coverage. The more coverage we get, the better. Right. So that's pretty much how regular FL feedback work. We will not go over it as we talked about it, but the idea is to instrument the actual binary. In the case of kAFL, the instrumentation is replaced with Intel PT traces. So the Intel PT traces are essentially translated to the bitmap, just like in the case of AFL. So as we discussed, the idea behind the setup is essentially that we have a fuzzer that executes on the host, and it fuzzes the target that is being executed on the guest, and they communicate via shared memory. The process pretty much from the host perspective looks like that. The host sends input to the guest and it overrides its panic handler. That's our resilience to crashes. And from the guest perspective, the guest requests the next payload. It discloses the CR3 register, which is the page table directory. We needed to focus on a specific driver, and it sends the panic handler address so the host can override it. Here you can see a basic example of how a harness would look like. This first part, we pretty much just open a handle to a device, and we allocate memory for our buffer. And in the second part, as you can see, what I described earlier just in code, we disclose the CR3 register. We ask for the payload buffer to be populated. We do some basic input validation, and eventually we run our input against the target. You can see that the mutated input here is the data and the size. Okay, so just to recap this high-level fuzzing section, we talked about the discovery of device name handles and ioctals, how we can generate a harness from a generic harness, talk a little bit about grammar, and describe the kAFL setup in general. So just a few words about what next. We want to try and attack other operating systems. We definitely want to develop our take on grammar, and perhaps we're thinking about hypervisor as they offer more privilege levels. So yeah, we know there weren't many memes, so here's a lot of, we're aware of that and we're sorry, so here are a lot of memes for you. Some credits for all the great work we relied upon. And thank you very much for listening, and we'll be happy to discuss if you have any further questions.